Hello, this is Nicholas Evancich from Trusted Science and Technology. I'm here to provide you all with a seL4 overview and tutorial. So our agenda for today is an overview of seL4, the history, the capabilities, threads, booting, the security space, and then we're going to do a tutorial which will have a code walkthrough, running seL4 test, hello world, and capabilities. So what is seL4? So seL4 stands for Secure Embedded L4 Microkernel. It's the world's first microkernel that brings a formal proof of correctness, which we'll talk about in detail in a few minutes. The kernel was designed against a specification, and the translation of the source code into the binary representation holds a functional correctness proof. So what does it prove? So if we look at the ARM version, the binary code of the ARM version of seL4 correctly implements the behavior described in its abstract specification and nothing more. So what it does is the ISA for ARM is equal to what the kernel expects it to be. So the specification and the seL4 binary satisfy the classic security properties called integrity and confidentiality from the CIA triad. So the way that those of us that work on seL4, we define confidentiality as a system's effort to keep their data private, and integrity ensures that the data has not been tampered with and therefore can be trusted. So these are two very, very important behaviors to keep in mind when we're talking about seL4. So what is a microkernel? Microkernels have been around since the early 70s. They were coined in 1981, mostly from Carnegie Mellon. And a microkernel is basically the minimum amount of software that can provide the mechanisms needed for a higher level OS. So what do we need? We need low-level address space management, so we need to be able to handle memory. We need thread management, more or less a scheduler. We need to provide inter-process communication, so the IPC has to be able to move from thread to thread or process to process, however the microkernel handles that. And then you need to be able to handle IRQs. Another tenet of a microkernel is generally the kernel is the most privileged thing, which obviously is different in monolithic and hybrid kernels, but in microkernels, the kernel is the ultimate arbiter of what's happening. So what are the pros and cons of a microkernel? So the advantages of it are, it can be, if you're looking at it from a server point of view, they can be plugged and swapped and restarted easily. So your kernel is below all of the other services that are running on it. So you can pull it out and put it back in as needed if it crashes or has an error or whatever. From a security point of view, which we will obviously spend much more time talking about, we Microkernels provide separation of address spaces that are managed by the kernel, which is not true of hybrid and monolithic kernels. So generally speaking, your microkernel will have very few lines of code. So in seL4's case, it's about 9,000 lines of code, which is one of the reasons that it was able to be formally verified. A much smaller code base allows it to be easier to create unit tests and be peer reviewed. Since all of the drivers live in user space, they cannot directly crash the kernel. So most of the blue screens that a lot of us experienced in Windows, they weren't really due to the Windows kernel crashing. They were due to a driver causing a problem in their kernel. This can't happen in seL4. So the disadvantages, number one is there are more context switches. So because the system calls are really mediated by the kernel and viewed for capability security, which we'll talk about in a few minutes, the context switches are expensive. And you also have to, everything has to, by definition, cross from user to kernel space. So if you write a Ethernet driver in user space, which of course you have to, that Ethernet driver now talks to everything else via the kernel, which just slows everything down. You also don't get process management for free or easy. So the developer has to manage the process space. And then finally, the ecosystem and the accoutrements just simply aren't there for microkernels. So you know, if you want to build a version of VI, most likely you can't just grab the source and build it and run it. So it'll take a lot of tailoring to get something like that to go. So common characteristics of microkernels are everything lives in user space and everything talks through IPC. And the benefit of that is you get a very small kernel, which is amenable to be formally verified. But I mean, excuse me, that also gives the kernel a very limited set of responsibilities. Important responsibilities, but limited nonetheless. So there is a long history of people building microkernels. So obviously there's the L4 family, which is what we're going to talk about here today. There's GNU Herd, there's Minx, QNX from BlackBerry. So a bunch of other people have built operating systems on top of microkernels. So seL4 isn't the only set of developers that have done that. Again, the unique feature is they formally verified it. So seL4 is derived from the L4 family of microkernels. So it comes from around 1993. It has been generalized because not all of the L4 kernels use the original base. So the L4 kernels have a long history of branching and having different implementations. So our Data 61 friends from the University of New South Wales, they were the first group to focus on taking the L4 microkernel and make it embedded. They looked at much smaller memory footprints and lower complexity. So they enacted rules on how to develop these things, which made it amenable for formal verification. So OK Labs spun out of University of New South Wales, NICTA, with a commercial offering of L4, which was called OK L4, and that was around from 2006 to 2008, and it had capability-based securities. So the point of this slide is the L4 family has a long history, and there's also been commercial offerings from it. So they all basically share the same basic mechanisms and concepts. So address spaces, threading, schedulings, very thin IPC. So seL4 was originally created at OK Labs, and it was implemented in a Haskell specification. So the resource access is determined by a capability model, which we'll talk about capability security models in a couple of slides. And the really novel thing that our friends at Data 61 worked on was this enables formal reasoning about an object's permission. So because the code base was so small and because they went with a capability model, they were able to apply formal logic to an object, and which is very novel, and they were the people that provided us with a formally verified kernel. So the next major thing that they did is they created a formal proof of functional correctness in 2009. And what it does is it proves that the implementation is correct against the Haskell specification, which we'll go into this in more detail in a few minutes. So it proves that the kernel is free of deadlocks, live locks, buffer overflows, arithmetic exceptions, and various other things, which we will go over the assumptions in a minute. The other major innovation that they've done, our friends at Data 61, is the formal proof of C to binary translation. So what they did is they created a proof that shows that whether or not there are errors in your compiler, GCC, or Clang, or what have you, it's immaterial to their functional proof. So one of the questions that we get as implementers and researchers in seL4 is, what does seL4 actually prove? Well, you have a kernel specification in red, which you have the kernel C code in green, and you have the binary representation in purple. There are equal signs between each one of those. And our friends at Data 61 were the ones that put those equal signs. So what we are saying is your kernel specification is equal to your binary representation. So if you make errors in your specification, those errors will be reflected in your C code and in your binary representation. So using formal solvers like Isabelle and those type of tools, your specification should be as error-free as you can possibly make it, which then translates all the way down to your binary representation. So your a.out has as few mistakes as you enter into your kernel spec. So that is what seL4 offers you, is you have a kernel that Data61 and other people have spec'd out, and the specification is equal to the binary representation. So as long as you are comfortable with what is in your specification, you are guaranteed to get that out of your binary representation. So what properties does this imply? So the 6 main things that we normally talk about in seL4 are you do not have buffer overflows. So from the kernel's point of view, buffer overflows just simply do not exist. You do not have null pointer dereferences. There are no memory leaks. So your garbage collection is taken care of for you to the most part. You don't have arithmetic overflows and exceptions. So if you're converting from an int to a float or a float to an int, then these things are already specified by a much higher level domain-specific language, and they're covered. You don't have undefined behavior. So this handles things like jumps and loops. And you also don't have general pointer errors. So if you have multiple dereferences to a pointer, seL4, the kernel, will handle that for you. This is assuming all of the assumptions are correct. So what are the assumptions that we make when we're working on seL4? Number one, we cannot get away from any amount of assembly. So the very, very small amount of assembly, I believe it's 100 lines and change in ARM, is written by hand, and it's good. So there are automatic and human checks, excuse me, that work to determine that that is a valid assumption. The next assumption we have is your hardware is working and it is within its spec. So if you have an MMU, which seL4 requires, your MMU works, and it's built to the specification that the rest of the hardware needs it to be. Next is hardware management. So things like cache and TLB are implemented correctly. So if your cache hits are leaky or bad, well, I mean, you have bigger problems than formally verifying seL4 on your system, but seL4 assumes that those things are correct. So boot code is effectively out of scope. We assume that the boot code puts the kernel into a known good state. Generally speaking, we use U-boot for everything that we do, mostly because it's open source, but also we have purview into it. The next assumption is DMA. So we assume that only the CPU and the MMU can directly access memory. So if you want to port seL4 to a system that has a flat memory model or some weird memory access or peripherals that directly write to registers or memory addresses, seL4, the proofs will not be valid there. The last assumption that we make is information side channels, they're not covered under the proof. So if you have the capability to do side channel analysis to some degree, the proofs simply do not cover that eventuality. That said, these are a very, very small amount of assumptions that need to be made. So most people assume, their Intel CPU is working correctly. Most people pay no attention to hardware management. And most people have no opinion on how their system is booted. So these are relatively easy assumptions to make. So we're going to talk for a couple of minutes about the capability security model. So seL4 uses a CSM, capability security model. So CSMs are a design pattern in trustworthy computing. And the basic idea is a capability is a key. And that key provides authority that references objects and provides certain access rights. So those keys are usually immutable but transferable, and they allow different processes or threads or objects to share different information. So one of the unique features of seL4 is it provides an implementation of this model with very unique features, which again have been formally verified. So how does seL4 work with CSM? So capability spaces are implemented as a directed graph of kernel managed capability nodes. We call them CNodes. You'll hear seL4 developers talk about CNodes, Cspaces, VSpaces a lot, and we'll go over those in this presentation. So capabilities form the nexus of security in seL4, and the kernel keeps track of everything in the capability derivation tree and the capabilities required for any operation on a kernel. So what does that really mean? So if a user space application wants to do something, it makes that request. That request is checked via the Cspace and CNodes, and it is either allowed or denied by the kernel. So this prevents bad actor threads from gaining access to a resource that they're not supposed to have. So from the offense side, this is one of the things that makes seL4 very, very difficult to hack. So you can definitely pop up a new thread, and that new thread needs to have the right Cspace and CNode data structures in order to do anything. So if it doesn't have that, then it will make a system call, which the kernel will just simply deny. So in seL4, capabilities are unforgeable, they're transferable, and they're extendable. So another thread could take a CNode from a different thread and add some new capability to it. So if a thread is monitored and malicious behavior is detected, the capabilities of that thread will be revoked, and that essentially ends its ability to do anything in seL4. So in seL4, there are a few related structures that we have to think about when we're talking about the capability security model. So one is Cspace, which is a directed node graph of CNodes. The next is a capability pointer, which is an address to a capability. The next is your Cspace path. And then, excuse me, there is CRoot, which is the beginning of the Cspace, which comes from the root thread in seL4, which we'll talk about in a few minutes. And then the final one is a Cspace node, a CNode, which is a table of different capabilities. The second main data structure that we have to talk about in seL4 are VSpaces. So VSpaces are virtual address spaces that are chunks of kernel managed memory that threads can use to run in. And they are completely isolated from the rest of the system. So the kernel manages these, and they provide virtual memory spaces for different threads to run in. So a thread must possess a capability, so it has to have a CNode that allows it to see this VSpace to a chunk of untyped memory, which it has the ability to retype as virtual memory to do whatever it wants. We'll talk about untyped memory in a minute. This virtual memory is associated with a thread object, and when that thread starts, it lives entirely in that VSpace. And there are very few reasons where it can leave that VSpace. So the idea here is a thread starts, it should, when it is created, have a capability space. That capability space gives it a certain chunk of memory, which it is untyped, and that thread has the ability to type that memory within the parameters that the capability security module gives it. So the memory objects are hardware dependent. So for ARM, what we're looking at are page directory entries, page tables, page table entries, and pages. These are all things that are very hardware dependent, and when we go and look at the code, we'll see that when we create the dynamic versions of the code, these things will be defined in there. So The other thing to understand about VSpaces is they're completely hardware dependent. So when you port seL4 to a different piece of hardware or a different board, most likely your main time is spent working in VSpaces. So untyped memory is the default classification of memory in seL4. So untyped memory is basically the blob that you get when you ask the kernel within your CSpace and VSpace for a chunk of memory. Excuse me. Untyped memory is required to be retyped into another kernel object. So this means that the thread that invoked the untyped memory needs to have the access to change it to something else. So you can absolutely set up your CSpaces where the thread that you created is unable to change your untyped memory. Obviously a bad idea. So you want to give it that properties. So when you change your untyped memory into a retyped thing, into an object that you care about, the kernel knows about it and keeps track of it. So you make a new entry into that directed graph of CSpaces, and the kernel now knows what this memory is supposed to do, what it's allowed to see, and what have you. So we're now going to jump into the kernel discussion. So the seL4 kernel isolates applications and provides primitive mechanisms for these isolated instances to communicate with one another. So what do we mean about that? So the seL4 kernel provides a minimum amount of capability that you can build user applications on. So the kernel is not interested in an Ethernet stack or a file system. It cares about scheduling, memory, capabilities. So that said, it's up to user space libraries to abstract these primitives and provide easier to use APIs. So if you want to write a file system for seL4, then that entirety is basically on you. That you get IPC, you get scheduling, you get memory access. End of story. And all of the I/O, all of the bookkeeping is up to you. So the kernel provides objects for threads, address spaces, IPC, notifications, device primitives, and capability spaces. Everything else is up to the developer, and it lives in user land. So all of these objects can be used in user space to interact with the kernel and other things in user space. So everything that you are working on in user space, when you want to do something that is kernel provided, so threads, address spaces, IPC, notifications, what have you, all of those hit a system call, which the kernel checks, and all of the security concerns with VSpaces and CSpaces come into play. So if you want a performant userland application, then you want to minimize the number of system calls that you make. If you want a very, very secure application, you want to maximize the number of system calls you make. So now we're going to talk about the root thread. So the root thread is the first thing that boots up from seL4, and we'll talk about the boot sequence in a minute. So this is essentially where the main function starts from, and it's what the other objects are built on. So everything derives from the root thread. So the root thread contains the original TCB thread control block, the initial VSpace, initial CSpace, and whatever IPC buffer you have. So the structure can be found in bootinfo_types.h. You can acquire the original boot structure from platform support get boot info, which will give you a user space boot variable that you can look at. The reason you might want to look at that is to determine how many cores you have turned on or what have you. So at this point, you can start allocating memory, creating newly minted capabilities, and a whole bunch of other wonderful seL4 things. So thread control blocks, TCBs. So seL4 uses threads to group contents together. So threads are contained by a TCB block structure. And as of version 8, go to that header and take a look at them. Every TCB has an associated Cspace and VSpace. Just like every other object, TCBs are created using the seL4 untyped retype. So what you're doing is you're taking a chunk of untyped memory and you're retyping it to be a TCB. The newly created thread is initially inactive, so it has nothing in the scheduler. And so what you do is you come in and you schedule it. You give it a priority. The next topic is endpoints, which is our entryway into inter-process communication. So endpoints allow small amounts of data and capabilities, so we can send a CNode across an endpoint, an IPC, to be transferred between two threads. So all of our userland execution elements in seL4 contain a thread, a CNode, and a VSpace, and they may contain an endpoint which allows for IPC. So they're invoked with send, call, receive, reply, receive, which are different mechanisms that allow for blocking or non-blocking. So one of the services that seL4 provides is inter-process communication. So IPC is the mechanism for thread-to-thread and thread-to-kernel communication. So you can either talk from your user space thread to another user space thread, or you can talk to user space thread to a kernel, which then may talk to a different user space thread. So IPC messages can either be sent to an endpoint, so thread to thread, or a kernel object. So because seL4 uses a capability model, the IPC requires that threads-to-thread communication has a capability that allows that communication to happen. If it doesn't, it's completely denied. So a way around that is sending communication to the thread, which then, the thread to the kernel, which then the kernel can pass it on to a different thread. So IPC goes all the way down into CPU registers. So those message registers are backed by the threads and IPC buffer, like in this slide. And please go to that code for further details. So as I said before, every IPC requires a capability. They also have badges, which please refer to the seL4 instruction manual for that. But if you want to send a message, you do seL4 message info, and this is the data structure. So you have a label, a message length, the number of capabilities, which the kernel will check, and the capabilities then get unwrapped. So when the message gets sent, the kernel intercepts it and determines whether or not this is a valid message. And then you again have the message registers, which the kernel uses for speed. So seL4 also provides notifications. So notifications are non-blocking signals that can be used as semaphores. So this is analogous to POSIX signals. So you have signal wait, pull, and bind on notification. So these are used for userland applications that need to do things like have a TCP stack or file systems. And this is the seL4 mechanism that enables all of those POSIX-like operations. Okay, so I promise we're getting to the end of this. So the next two topics we're going to talk about are the Kernel Boot Sequence, and then how the code is organized, and then we're going to look at some demos. So after the board is set up with a bootloader, which we usually use uboot, and execution is handed off to the elf loader, the kernel takes a look at, and again, I'm looking at the ARM version, boot.c. The first function that's called is init kernel. And it tries a bunch of different things to figure out what it's supposed to be doing. So the important part is try init kernel. And in that, several important things happen. So the first thing that happens is we set up the virtual memory. So when you're porting a new device to seL4, this hardware.c is the first thing that happens. So what we do is we map the kernel devices. So everything that the kernel requires to boot, and similarly the CPU requires to boot, happens at hardware.c. Inside of that, init_CPU happens, and it, tells it if it's 32 or 64. And in ARM, you can take a look at that VSpace.c, and that VSpace.c is, as the previous slides in the presentation have showed, that is one of the integral parts of the entire seL4 boot chain. So a lot depends on VSpace.c. Then we set up the stack, and then we turn the timer on. So the next thing that happens is we initialize the platform. So we turn on IRQs, turn on L2, and then whatever other platform initializations that are required happen here. So like low power or what have you. The next thing that happens is we create capabilities for the root environment. So we set up the Cspace for the root thread. The boot info frame is allocated and initialized. Initial address spaces are created. The boot info frame capability is created. So the very first thing in that Cspace is our boot info frame capability. We create the threads for IPC because we want the root thread to be able to communicate with whatever we're about to set up. And this is all brought together by creating a TCB, and we do it with create initial thread. So at this point, we have a root thread running. We have capability spaces for the things we're about to turn on, and we have TCBs for those threads. Then we blow away the L1 cache, which comes from the formal proof, and then we return the execution. All right, so I appreciate everybody sitting through all of that. So what we are about to do are a series of demos, which I'm going to go through and follow the agenda. So the first thing that we're going to do is navigate the code base. So when you run into a new and complicated code base like seL4, one of the things that I personally like to do is get a view of it. And I use cscope to do that. So as you'll see in seL4, everything is handled via a repo manifest file, and it works like a standard Linux program. So this is what a standard seL4 project looks like. I believe this is seL4 test, which we will go through in detail, and this is the output of cscope. So if you're ever confused, the main source code is in kernel and projects. The kernel is where all of the kernel code that we've been talking about for the better part of an hour is listed. And projects is where most of your work will be done. So with that, I am going to move over to doing some demos. So thank you for your attention. Okay, so what we are going to look at is seL4 test. In this virtual machine, I've already set up the seL4 environment, and I've downloaded seL4 test, so please follow the Data 61 instructions for that. What I would like everyone to focus on is this window. So what we are going to do is build seL4 test and then run it and look at where the output, where it is generated from. So the steps to build seL4 test is first to create a scratch directory, which then we will dynamically generate the input to that directory. We will build it, and then we will simulate it. We'll run it in QEMU. seL4 test is very useful. So first of all, it will tell you if your build environment is set up correctly. So it's something that you want to run after you follow all of the Data 61 directions on how to set up your environment correctly. Also, if the project you're working on stops working, going back and running seL4 test is a good way to tell whether or not the problem is with libraries or your build environment, or if it's something that you made a mistake with. So if seL4 test runs and your code doesn't, then chances are it's whatever you're doing. And then finally, if there are upgrades to libraries or build tools, seL4 test is a excellent sanity check to determine whether or not the problem is with the libraries or your build environment. So the first thing we are going to do is create a scratch directory. So in this case, we're making a Intel 86 version. So we make a scratch directory, then we cd into it, and the next command we run is going up one layer. It's running init build, and we're telling that the platform is 64-bit x86, and we're going to simulate it. We're not going to run it on real hardware. So before I do that, what I would like to do is show you that this directory is perfectly clean. So if we run this command, what it does is it adds a bunch of dynamically generated files to this directory. And our next step is to build it with Ninja. So Ninja is a fast build system that relies on higher level build systems, make systems to operate. So in this case, what we're feeding Ninja with is CMake. And if we look, we now have some very important things. One is GDB. So if we want to debug this, we can go into GDB to do it. What we care about here is simulate. So what this will do is take the ELF that was generated, and it will run it in an x86 QEMU on this VM that we have. So this is seL4 test running. And what we are doing is we are running through a bunch of unit tests that test the validity of various things that we claimed in the definition that we made when we did the /init. So this will take about a minute to run. And once it's completed, we will see the magic phrase that all is right in the universe. And so as you can see, it's running various tests, and in the Visual Studio Code window I have over here, I have some examples of how those tests are created, and we will talk about those in just a minute. So this takes a couple of minutes to run, and you can see your hello world scrolling by. And the server tests that just went by are what we're going to talk about over here. And you can see that 122 tests were passed, 54 were disabled. They were disabled because they're not applicable to this architecture that we were using. And then you see the magic phrase, all is well in the universe. So if this works, then your build environment is set up correctly, all of your manifests are pulled down correctly, and you have a canonical, ready to go seL4 setup environment. So we exit out of QEMU. So over here, so Data61 provided a bunch of wonderful macros that allow us to set up various tests. So here we are creating essentially unit tests, and they're all, as you can see, defined, in error, and then the data structure that we care about, and then the Cspace path, which we talked about earlier today. And what you're essentially doing here is going through and checking various conditions. So if these conditions are met, the tests that we just saw scrolling over in the terminal pass. And it runs through 100 and some odd of these. And so if you want to create more tests, you can add them into test.c, and using the macros that Data61 provided. You can also create your entirely own test structure and create a full-blown version of whatever set of tests that you care about. So, here, Data61 cares about a badged server with this C path. But if you want to test your Ethernet port, you can use this mechanism to do that and add it to seL4 test, which then you can again run to be sort of the canonical baseline to determine whether or not what you're doing is okay, and if you're breaking things further down the chain. So in summary, seL4 test is the first thing that you should run to make sure that your build environment is correct and that everything that you're doing works in the seL4 ecosystem. So for the next demonstration, we are looking at the tutorials provided by Data61, and of course we have to start with Hello World. So again, this environment has been set up correctly. It runs seL4 tests well, and I've pulled down the tutorial manifests. So what we are going to do is create a Hello World project. So we're running .init, and then the -- tut Hello World says that we're using that one, which has been specified in a CMake file. So if we hit enter and we look again, we now have a couple of new directories. So we have Hello World and Hello World build. So what we are going to do is cd into hello world build and do a ninja. And so it cranks everything out, and we get our wonderful kernel.elf that we will use to simulate in just a minute. And while that is running, what I would like to do is open up a C file. So if we go to tutorials and we go into hello world, not hello world build, we get main.c here, which we will modify in a minute. So we can .simulate this, and it does the normal setup of how a seL4 kernel works. And as you can see, we get hello world here. So once we've booted and dropped to user space, we're running this code over here. So we will exit QEMU. And so the first thing we're going to do is introduce an error. So we're going to drop the semicolon there, and we will save that file. And we will clean everything that we have, and we will rerun this to show you all what a GCC error from seL4 looks like. So as you can see, it gives us the normal GCC line number output. And so this is us compiling the user space stuff. So what we are going to do is change this. And fix the error. Do another clean. Build it again. And then we will do our simulate. And now we've written our very first userland seL4 application. And we've seen how errors are thrown in seL4. So the next thing we are going to look at are capabilities. So again, the environment is set up, the tutorial manifest has been pulled down. Please follow the Data61 instructions in order how to do that correctly. What I'm going to run in the tutorial directory is int solution capabilities. So when Data61 wrote these tutorials, they leave the exercises up to the developer to work on. But they also provide a solution. So if you do -- solution, you get the version that Data61 believes is the correct version that will build and run. So what we are going to do is look at some capabilities in action here. So again, if we do an ls, if you notice, we now have capabilities, which is where the source code for the thing that we are about to build lives. And we will move into capabilities build, run our favorite ninja command. And once this is done, we will simulate it. So again, we have left the kernel space here, and we have created a 64K CNode, and in that CNode, a Cspace has 2K slots. And what we're doing is attempting to copy, mint, move, or mutate, which I've discussed before. That is invalid. And because it's invalid, we suspend the thread that is trying to do that. So over here in the code, what we see is this based on to check to see if the last CNode move slot, is empty. So it isn't. And that fires off this printf, which is here. And we use this thread control block to suspend the thread that is trying to do this. And we never reach this. We never reach this log message. And if you notice, we never reach any of these other fail states. So what happened here is we had a bad invocation, and we're unable to recover from this invocation. And because of that, we suspend the thread that tried to violate what we were trying to do, or what our rules were set up to do.